Good morning, good afternoon, everyone, and welcome to another ARA Webinar Wednesday program. I'm Jerry DiMaggio, and I'll be serving as your moderator for today's webinar, which is entitled Resilient-Based Design, Improving Reliability Under Uncertain Conditions. Before I introduce our speaker, I'd like to remind you that you'll receive a PDH certificate if you attend the entire program today. It'll be about 1 hour in length as usual. We'll have about a 45-minute presentation. It'll be followed by about a 15-minute Q&A. You'll also be entitled to receive a PDF version of the slides that you see in today's presentation. Now it's my pleasure to introduce our presenter, my very good friend and colleague, Dr. Ahmed Al-Hassan. Ahmed is a principal engineer at ARA within the Research and the Technology Deployment Group. He happens to be the group leader, has over 10 years of experience both with industry and in the academic university environment. He specializes in geotechnical asset management, pavement performance, evaluation and management, resiliency-based design, and statistical analysis and probability theory with regard to artificial intelligence applications. Dr. Ahmad has led numerous projects and authored over 70 technical papers, webinars, research reports in a diverse range of tropical areas.
All right. Thanks a lot, Jerry, and thanks for the introduction. So in today's program, as Jerry mentioned, we will be discussing resilience-based design, which is related to the big picture of resiliency. Everybody is interested in the topic as we have more and more extreme events. So this is the outline of the presentation today. It's more of a discussion, actually, so I'll try to keep it light as much as possible, and we'll cover as many topics as I can. So starting with resiliency in geotechnical and its role in geotechnical practice. So the question is, why resiliency? And first of all, I know everybody is looking at it nowadays, and there's more and more interest and probably requirements in the future to include some aspects of resiliency in design and management applications. But the more fundamental question, or the more fundamental answer, is there are increasing number of extreme events. And we all know that due to climate change, that's one aspect. But there's also the fact that extreme events will accelerate the deterioration of assets. And when we think about extreme events, and here the terminology will maybe change from slide to slide between extreme and disruptive events. So it's sort of unexpected, or it could be expected and planned for event that we're trying to accommodate, or the asset is trying to accommodate. So this will accelerate the deterioration of the assets, and there is an increased demand as well. So that's another aspect. So maybe the events themselves may still be the same, but given the size of the networks that we have and the number of assets that we're trying to manage throughout the US and other countries. For example, the picture in here is from Canada, and it's showing some kind of failures, obviously, from a flood event. And that increased demand and the increased number of assets that we're trying to manage is raising the question of how do we keep the network operating given all these disruptive events. There is also the fact that we have an aging infrastructure that needs a lot of maintenance. It's not as strong as it used to be, probably. There's more deterioration going on. And this last photo in here is intended to show that extreme events, again, it's not only floods, it could be other extreme climate-related events, or even impact loads that we know about from before, but maybe we need to reconsider the way that we handle them. This is also a multidisciplinary concept. So that's also one other, I would say, non-tangible benefit from resiliency and considering these aspects, that there is more collaboration, and it will help break the silos that we typically face within the agencies, transportation agencies, between different areas of practice. So here are the definitions out there for resiliency or resilience, and I won't spend too much time on it because I've introduced that in a previous webinar and it's all over the place. But it is important to remember that resiliency or resilience can be simply defined as the ability of a transportation system, and here we're focusing on transportation, to absorb disruptive events gracefully and restore its pre-disruption level. And we will talk about that of service in a specific time frame. There is also it's not a clear definition, but you can compile the definition from the bipartisan infrastructure law, uh, that it is the ability to anticipate, prepare for, adapt to conditions, or withstand, respond, or recover rapidly from disruptions. So as we can see in the second definition, there are more aspects to it. It's not only about the design, it's not only about the ability of the asset to withstand, but it's also about the planning for it. That's part of the big picture on resiliency as well. And also one other thing that I would like to add, that resiliency doesn't necessarily stop at physical assets. It could also include non-physical assets that support the transportation network and leads to basically the maintenance of the network. So also, in addition to that definition, we have to think about scale. So when we talk about resiliency, it depends on the scale that we're trying to apply it for. So some people look at resiliency from a network level. And as you can see here in the picture, this is actually comes out of a project that ARA completed. My colleague Young Lee actually completed this project with the team at the time, related to the resiliency of pavements in Florida. So you can think about it at the network level or system level, and this is how resiliency started, because part of it is that you have redundancy in your system, that your system overall can maintain its performance and come back over time. So there's also the network resilience. Again, for transportation assets, there are different requirements and measurements or measures that we still need to better define. But if we zoom in, there's also the next level of detail, which is what I call localized systems or localized assets. And we'll talk about these in a basically throughout this presentation. And if we zoom in even further, we can get down to the element level. And that part, when we discuss resiliency, for example, for a single foundation, then there is a need for a different style or approach to resiliency. At the grand scheme of things, I believe that resiliency or a robust framework should be able to capture all these levels through different processes, not necessarily through the same process. There's another photo in here showing basically the use of deep foundations to stabilize the slope, coming from a previous study published in the DFI by Jamal Nusayrat. And it talks about, it wasn't about resiliency at the time, but the reason I'm including this in here, because it is one of the ways to improve stability of some of the geotechnical assets. And again, we'll talk about a similar case study that was performed related to slope stability. So resiliency at the asset level or localized system is basically when we discuss a bridge, for example. The bridge itself has different components and it will interact with different elements or parts of that bridge and the surrounding assets supporting that bridge. And that's just an example. You can think about resiliency for pavements, for embankments, for different applications. But what I refer to as a localized asset is basically that system where you can consider it as a one entity, but it's composed of multiple assets in some occasions. And resiliency starts actually from the planning stage and site characterization, since we're talking about geotechnical resiliency in here. So it starts with site investigations and site characterization, moves into the resilience-based design, which is a framework that we currently don't necessarily agree on, or we don't have an established framework for it. And that's the purpose of this presentation. And then the geotechnical asset management aspects of it as well. So one important component with resiliency and geotechnical resilience specifically is to consider the management aspects, maintenance impacts, and how to adapt for changing conditions. We can predict as much as we can, but eventually things will happen over the life of the asset. So we should be able to provide additional support and improvement strategies throughout the asset life. Here's the typical resilience components chart, and this is again, it was introduced before, but what I want to deliver out of this one, that if you look at it in the plot here to the right, you have a performance on the vertical axis. That's basically what you're trying to maintain at a high level. And then you may have a disruptive event. And then at that time, your assets start losing performance or reduced its performance. And then it comes back, but it doesn't necessarily come back to the original condition, because that disruptive event will accumulate damage in most cases. Sometimes you may, or the asset may come back to full performance, but we'll talk about that throughout this presentation, that typically we see some cumulative damage, which is not typically what we think of in geotechnical engineering. Now, the components, some of the components that can go into resiliency, and these are not the measures necessarily, are the robustness of your asset, its ability to basically, how far does it go? And then rapidity as the time to recovery um, for that, from that disruptive event, to come back to the original performance intended. And then there is the resourcefulness and redundancy of the system, and these will impact the time of recovery or time to recovery. So these are not necessarily the final measures, but these are the components to consider during the resilience-based design. Now, to some definitions. So when we talk about geotechnical assets, we have been thinking of multiple aspects. Condition. Condition is basically, in this study, basically reflects the physical condition of the asset relative to its condition, original condition when it was constructed. So as you can see here, some of the photos showing an approach, a bridge approach with a basically a wall that is deteriorating. So that condition is dropping down. There's some deterioration going on to the physical asset, but not necessarily going to affect the performance at the beginning. So it may hold its performance at the same level, but its condition is dropping down. And that will eventually lead to reduction in performance. Performance is basically the relation, or it's the it relates to the intended purpose of the asset. So it's important to distinguish between these two, because it describes the cumulative damage concept, which is not necessarily always applicable in geotechnical engineering, or not typically used in geotechnical engineering. Now, the third point is the capacity, which also relates sometimes to performance. It's how much load, it could be force or it could be traffic, the asset can withstand before it reaches a limit state. It could be serviceability limit state, or strength, or ultimate limit state. So that is the capacity, and it also relates in some sense to performance and probabilities of failure. So these are three different components. This figure in here comes from a previous paper describing the movement or progressive failure of basically slopes. And it is important to notice that things do happen over time. And in geotechnical engineering, we understand that, but it's sometimes hard to quantify it and to label it as deterioration of the geotechnical feature or the geotechnical asset, but it's happening in there, and we need a better understanding on how to basically quantify deterioration of all geotechnical assets. Now, the next topic is going to focus on the load and resistance. And then here we're getting more into the design philosophy, or getting closer to this design philosophy. So whenever we're doing design, it could be structural design or geotechnical design. We have to think of multiple components. One of them is the limit states. So we have to understand the limit states that we're trying to address, and we have to define failure. And that by itself is not as easy as we can think of. So failure could be a total failure of an embankment. Let's say it collapses, that's a total failure. But what about the deformations that happen over time? These are serviceability failures, and the requirements there need to be considered when we design. And there's also the idea of marginal performance. So marginal performance is also an important aspect that we should start considering more frequently when we design. And that is the stage, as you can see here to the right. This is the plot when you're trying to optimize. And again, it depends on how you define the axes and the direction of the axes, but these are the variables that define basically the safe zone or the failure domains and the safe zone. So the assumption in here that the safe zone is below that kind of arch. And there is a marginal performance zone when we design. And typically, this zone is not very well defined in geotechnical application, but this is where your maintenance activities can bring your asset back to the safe zone or closer to the optimal design stage. So over time, your asset may start here where you optimize your design, but it starts moving over time towards the failure domain. And once it reaches the marginal performance domain here, the shaded area, you have a chance to perform some kind of additional maintenance to bring your asset back. And moreover, you can have some kind of preventive maintenance also throughout the asset life to make sure that it doesn't go into that zone in a cost-effective fashion. So cost is also aspect that we consider typically in the design and should be considered for maintenance activities. Now, the second or the next part is defining disruptive events or loads in general. So I will start with the argument that we have, in some sense three overarching approaches to defining loads. The first one is to look basically at a load history. That could be an approach, or you can forecast or estimate your load history. And you start looking for peaks, just like these ones shown at the top here, if you can follow my cursor. So you typically, in the old-fashioned design where you have a deterministic design approach, you just define the peak. And in here, we're talking about rainfall. Rainfall can have a transfer function to the water table, and then it can give you basically the impact on an embankment, let's say. Given the loads applied on it. And then you try to determine the peaks, and from that peak, you design for the most probable or expected peak value to make sure that your asset doesn't fall below that. But if you do a proper time series analysis, and this is an actual data, you can decompose that trend in here, the first one, into basically the repeated trend that is an average trend that happens almost cyclically every year. But then you will have some kind of a random event below that, which is the changes in the weather. So you can think about this whole data as climate forecasts rather than weather, and then you have the individual weather events. Now, as you can see, there is non-stationarity in two senses. The first sense that it goes up, there is an overall increasing trend here. So that indicates that there is a climate change impact over time, but also the other non-stationarity that is not necessarily clear here. Some of these events happen too frequently and close to each other. And when you have close events happening, it can lead to basically a whole different type of floating condition that you didn't account for in the traditional sense. So in the, let's call it the allowable stress design approach, maybe we can think about it this way. You look for a peak, you design for it. In the LRFD approach, you can take all this history and try to compile it into a probability distribution and have a probabilistic description of your load. But in a resilience-based design, we should consider the stochastic scenario and learn from the past data, forecast into the future since we have a trend. It's an unstationary trend. Forecast into the future and consider the full scenario or scenarios that you can predict in the future for these events. So the bottom line here is learn from the past and forecast for the future. It's a very simple message, but it's important to consider stochastic aspects of it and include that in the design stage. So in here, this is a typical plot, and we have seen something not necessarily similar to this plot, but the idea of reduced capacity over time. So in here, you have to the left axis, the vertical axis is performance, and to the right axis, vertical axis, it's capacity or ratio of resistance to load. And over time, your capacity, the capacity of the asset, will start going down. However, for design purposes, your capacity requirement is down here. And we typically design with a factor of safety, so we typically expect the asset to have full capacity for a certain period of time. But over time, with deterioration and movements, that capacity can drop, and you can start reconsidering the traffic loads and how much your asset will handle or will be able to handle. And at that stage, the performance will drop into a marginal performance stage. Now, that performance in here is a step function. It could be a continuous function as well. So in geotechnical engineering, it's not as evident as some other assets, such as pavements, where you have increased roughness or reduced ride quality over time. In here, it could be, again, the capacity, how many trucks you can handle, or how much maximum load that embankment can handle, or the subgrade can handle, and that can reduce. And there are two aspects to this if we talk about an embankment, let's say. For an embankment, the capacity could be, rarely it could be that the capacity will totally fail, but it's rather the subgrade that is deteriorating over time and impacting the pavements supported by that embankment. But also, again, the capacity for the entire embankment could be also a consideration for that aspect as well. So the next component that I would like to talk about is system response. So instead of resistance, typically in the load resistance factor design, we consider the load side of the equation and then the resistance side. The resistance side is simple, typically in the sense that you can do engineering analysis for that capacity of the material. But a response, an idea of a response, it includes basically the multiple components, again, condition, performance, and capacity. And it's not only the engineering asset, the engineering analysis, whether that asset will withstand a certain load level, but it's rather how it performs over its life cycle. So system response is actually the other side of the equation besides the load, and it's how that system will react to the applied loads and the disruptive events throughout the life cycle of the asset itself. And again, in here, you can see the capacity ratio goes down. This is part of the system response. Then you have the cumulative damage, where you can accumulate deformations in certain geotechnical assets, or sometimes change in the properties. It could also be part of that cumulative damage aspect. So it is an easier thinking process if we want to consider deterioration, because talking to geotechnical engineers, deterioration is a little bit of a foreign aspect, except for structural foundational elements that goes into the asset, but the asset overall can accumulate damage. So quantifying damage accumulation and damage functions would be an easier approach to understand that deterioration process. Now, with all these definitions, let's jump really quick into the design philosophy. And the first aspect to the design philosophy is the definition of uncertainty and uncertainty or variability. We have two aspects when it comes to geotechnical engineering. The first thing, that in many cases, geomaterials are variable spatially, and they can also vary, or their behavior can vary over time, depending on, as I mentioned, climate impacts and weather events, and all of that can change the characteristics. So that aspect is considered variability, and it can be part of the overall picture of uncertainty. And uncertainty can be due to the inability to describe or quantify an event. There's a lot of complexity, and that would be considered a chaotic behavior. It's not necessarily a random behavior. We can understand it if we have enough time and resources, which is almost always a challenge to spend too much time studying one aspect or one project. So it can be described under the bigger umbrella of uncertainty. And then there's the known events, or list of events that we know their basically happening, but we're not sure about when they will happen or how severe they will be. And that's where the forecast, as I mentioned before, in the loading conditions uh, comes in. So you forecast for the future and you put in multiple possible scenarios to see how these different events and the sequence of events will affect the asset itself. And there's the unexpected events. And these typically we do not understand and we do not necessarily know. And that's where the design philosophy needs to be flexible. So typically when we think about design, it is a rigid design. We have a loading condition, we have an asset that we're trying to design, and then we come up with the most optimal, I would say, solution. Too much or over design can be expensive. So the way out is to have that flexibility in the design process and think about the asset as a long-term asset that has multiple stages in its life, and it can incorporate maintenance all the way from the design stage. We can start thinking of possible maintenance activities and improvement activities that can adapt for changing conditions. And then there's the last known but overlooked uncertainties, and these are basically, again, multiple reasons for that. Sometimes the resources are not there. Sometimes we are not sure how to handle these uncertainties, and we overlook them or we cannot simply handle them. So now for the first generation, and that represents in some sense the allowable stress design, stress design philosophy. In here, we have distributions. In the deterministic design approaches, we don't necessarily have a distribution, but we know it's back there in the background. But our approach to the design is to use the means or the average, and then try to have a reasonable safety margin that will keep the asset in a safe state as much as possible. Over time, we realized that this is not the most effective approach, and we started looking into reliability-based designs, such as LFD or LRFD. And in that case, we start looking at the distributions of the applied loads and the resistance. So Q here to the left is the applied load, resistance is the distribution to the left, and we're trying to minimize that overlap in here, which is a probability of failure for that asset as much as possible in a cost-effective manner. Now, one thing I want to point out that in reliability functions, the original definitions of reliability, it is a function of time. So time should have an impact. The way that we can think of time in the more traditional fashion, again, we look at the possible events out there, compile them into a probability distribution like this one, and then we design for it. However, the sequence of events will change how the system respond. So that's where the idea of system response instead of resistance comes in, because system response can account for the sequence of events, unlike when you compile everything into a distribution describing the resistance in there. Now, to improve that design, you have two options: either make it larger, make it more resistant, and separate these two distributions, but still there is that possibility of failure or probability of failure. And the other approach is to improve the certainty in your designs and in the resistance side, and that would basically also reduce the probability of failure. However, with a reliability-based design, this is an oversimplified curve. What we should start thinking of is the life cycle of the asset and try to maximize under probability. So this in here is the average of that performance curve or condition curve and performance. And what we are trying to achieve is to maximize that time span where the asset can meet the performance requirements and also take into account the disruptive events, the sequence of events happening, not a single point, and not consider these as independent events that do not affect each other. And with that, we try to maximize the area under the curve in some sense. And this in here by itself is a challenge. So the area under the curve related to condition or performance, it's really hard to define also for geotechnical assets. So there is more work to be done in this area to have a better definition of that area under the curve. Now, I kept talking about repeated events and the sequence of events. So let's go into a case study. This is a hypothetical case study where we have an embankment or a slope, and it supports a road and at the middle here. And if you consider the peaks, as I mentioned before, and you take the maximum peak, let's say this would be your water table level. However, if you consider repeated rain events, and that happened over and over, by the way, one of the scenarios that we was famous was in Vermont, basically in 2023, where repeated rain events led to an increased water table that was not considered by anyone at the time. So when you have repeated events, the overrun reduces and they are short, not necessarily flood events. So your riverbank doesn't go up and then starts flooding the other assets. It's the other way around where you have repeated rain events slowly, day over day, and that soil in here gets saturated over time. You don't necessarily see any warning signs of flood, but all of a sudden, at some point, your water table goes up and leads to a failure. So when you do the analysis for the typical peak design case, you come up with a probability distribution function here for the factor of safety. Again, a reliability-based design should focus more on the probability of failure, but that's a more detailed discussion. And I will limit the discussion here to the factors of safety. So it was basically um, a reasonable design, let's say, and the factor of safety was 1.5, and this was actually an acceptable. So this is a hypothetical case study building on an actual case study that we have looked at. So it meets the requirements of that state, which means it is a reasonable design. However, if you consider the sequence of events and you start doing stochastic simulations and stochastic repeated runs, you end up with basically higher water tables leading to reduced factors of safety. And the probability of failure will be much higher at that stage. It's 7.8 compared to 0.6 in the previous one. And then the reliability index drops and the factor of safety drops. So the idea in this case study was to look at possible solutions, and one of them was deep foundations, similar to the case study showed at the beginning. So you can improve the resiliency of that slope here by introducing basically deep foundations. Now, is this study complete? Not necessarily to the full scale, because we have a lot of work when it comes to resilience-based design. We have to define the proper resilience measurements, quantitative measures. We have to define the impacts on network, and we'll talk about that in a second. But the improving strategy in here brought back the factor of safety, and again, related to this case study, the actual case study, there was an evident movement of that slope over time, and there were serviceability issues noticed, and that reflects basically the reduced factor of safety. So that's also another aspect that sometimes reduced factors of safety can lead eventually to a total failure, but it could also be an indication of a progressive failure leading to serviceability issues early on in the asset life, and then leading to potential total failure. Now, going back or zooming out again to the bigger picture of improvement strategies and improving resiliency of an asset and the network, actually. So first of all, resilience-based design will improve the asset robustness, similar to the example given, but also there are other aspects to be considered when we talk about the bigger picture, as the improving the network redundancy. That's something that we as transportation engineers generally understand, providing more traffic channels that can basically help provide services at the network level during a massive disruptive event. Maintenance effectiveness evaluation, that's something that we really need to understand, and maintenance activities are not always well defined for geotechnical assets. That's also another area that can help improving our improve our understanding of resiliency, but also improve the resiliency at large. Reducing consequences by improving support elements. So sometimes the solutions are not necessarily changing the entire asset or redesign the entire asset. Thinking about a more flexible mindset for geotechnical assets, there are some improvement strategies that can be taken during the service life of the asset if we have increased disruptive events or increased loads that were not expected at the beginning. Also, when we talk about network evaluation and even for an individual asset, return and risk analysis and improvement decisions is very important. So risk management, even though I didn't mention it here, but we've used it several times in previous webinars, is an integral part of resiliency and resilience-based design. And then also the bigger picture, connect the geotechnical resilience-based design, GRBD, to sustainability. So to overall improve the future of these events and try to help in reducing the number of disruptive events. Sustainability is a big component, and I'm not going to cover sustainability in this discussion, but it is an important aspect that should be considered for the future. Now, some of the concluding remarks and future directions we have for this study. Resilience, first of all, resilience is built throughout the project life. It starts from site characterization to design to management. It's not a one-shot deal, and we should reconsider our design philosophy to become more flexible throughout the service life of the assets. There is a need for more well-defined quantitative procedures, such as resilience measures need a better definition out there, and that's something that we are working on. Disruptive events are not limited to climate impacts. So even though the focus is on climate impacts, but disruptive events can also be correlated sometimes, or their consequences can be correlated to climate impacts. So when you have higher water tables, you may not see an issue with the water table itself, but rather the disruptive events happening during such extreme events can lead to massive consequences. A geotechnical resilience-based design approach should encompass previous requirements and consider the bigger picture. So the idea in here is not to basically dismiss all previous design philosophies. Definitely not. The idea in here is to build on them and improve the overall reliability of an asset and a system for the future. Geotechnical resilience-based design and resilience-based design in general will require extensive loading and response models. And these models need, it's big data, not bug data, and emerging analytical tools. So there is an aspect that we are also working on related to AI applications. So for resiliency, as we've seen, stochastic loading conditions and stochastic response models, these are time consuming and require a lot of analysis. So a physics-based AI approach, that's something that we are considering now, is very critical because with these approaches, you can run a couple detailed scenario analysis and then try to extrapolate following the physical procedures. And that's why I re-emphasize it's physics-based machine learning or AI application where you can build your forecasts in a more accurate way. And we should finally consider more flexible life cycle models with planned improvement strategies. It is very critical for geotechnical applications and all other applications in general, but I would say, and I don't want to claim anything, but I think the pavements management practices already have a lot of work related to maintenance. So there is, I would say, better improvement in that area for pavements. But for geotechnical assets, we do not always discuss maintenance activities and improvement plans for the geotechnical features or assets that we design. So that's something that we as geotechnical engineers and geomaterials engineers in general, including pavements engineers, should start considering for the future. And with that, I'll conclude my presentation and turn it back, open it for questions and discussions.
Okay, thank you, Ahmed. Very interesting presentation. Um, it puts some meat on the buzzword sustainability and resilience. So that's what we like to see. I would mention, and even though you focused on geotechnical features from an illustrative point of view, it should be clear to everybody who joined us today that resilient-based design is applicable to all kinds and types of infrastructure features.
This whole discussion, and you know me, Jerry, I'm half pavements engineer, half geotech. Like this whole discussion started with pavements, and it builds on that as well for geotechnical assets. So.
Okay, so before we get to the questions, and we already have several questions we'll get to momentarily, I'd like to share with you, as we always do, a few of our upcoming webinars. We've got programs set up on a monthly basis through the end of 2024. So those of you who are new to us, you can register for any of these webinars at the address that you see here. On June 5th, and we always have our programs at 12 to 1 p.m. Eastern Time. We just talked about an emerging technology, resiliency-based design. Now we're going to talk about, on June 5th, a older technology, we've been around for quite some time, use of permeable pavements. All of our presenters, as you've been told in the past, are ARA employees. And in this case, our speakers will be on June 5th, Lori Strauss and Dave Hine. Dave will work with us for many years. He's retired right now, but we still consider him part of the family, so he meets our criteria. Now, I would add that what they're going to cover, since it's got a very short title, they'll be addressing the ability to assess the benefits, costs, the effectiveness, and the limitations of permeable pavement designs over a diverse range of pavement considerations, because project specifics are very important. I don't typically do that, but with the brevity of the title, I thought you'd be whet your appetite a bit more. And then on July 31st, so you've noticed we'll have this June 5th webinar really only 2 weeks from where we are today. That's because of the Memorial Day holiday. And we'll go back to our usual schedule of the third or the fourth week in the month. On July 31st, we'll be speaking about transforming how we teach and learn, adopting immersive training, creation, and deployment. And our speaker with my good friend, Willie Morris. So Ahmad will address as many questions as we can during the time allotted. And then he's been gracious enough to offer his email address. So for the next 24 hours, please ask questions that we don't get to or you formulate following the program today. So the first question is, can you provide an example of how physics-based AI was utilized? And if you have any reference papers, that would also be helpful.
Sure. So, as for the reference papers, let me start with that. Um, this is an emerging topic or area when it comes to AI or machine learning. In this example or this presentation, we didn't really show or perform the full-scale physics-based AI. It requires a lot of work and calibration. But overall, the idea behind physics-guided or physics-based AI is to have penalty functions and boundary conditions on the AI algorithms that follows or obeys the physical rule and physics. And with that, you embed your physics rules and boundary conditions and differential equations into the optimization process of the AI algorithm. So we are still building these algorithms. It requires a lot of effort to dig deeper. It's not a black box at all. We have to build the algorithms from scratch. I'm not sure if there are ready packages out there, to be honest. And as for references, again, if you can send your email, I can forward some of the references out there in the area for you.
Okay, thank you. So the next question from Mir is how does resilient-based design work when a majority of the geostructures, specifically at local counties, towns, and even in some states, do not vigorously maintain a history of events or failures or mitigation measures or stabilization measures?
That's a great question, actually. So that's for a new state, let's say, or a new entity that is trying to apply such an approach. You can rely on a more, I'd say, national level database and try to extract these weather events and try to build on analytical models to predict your or forecast the behavior of your assets. And then from that, you can take it back and see how it affects its resiliency. And then the next stage would be, again, to rely on national practice, try to estimate some of the maintenance practices. Now, the other part of this question or answer there is, and it's already applied for some people, a Bayesian approach where you can keep an eye if you have a critical asset. You can establish a monitoring program that would actually allow you to maintain records of the response of your system over time, and then you can start building your improvement strategies over time. So that's an important aspect, the flexible design approach. At this early stage, I would assume that almost no one will have full records that can be used for resilience-based design, but it's a calibration process that will happen over time. One last thing, I'm sorry I'm taking longer, but this is an important question. Um, an important aspect is to avoid compiling equations over equations for calibration. That's where Bayesian approaches come in. And a Bayesian approach just keeps refining the original equations and the original models that you have built and improve your predictions over time rather than adding more layers of calibration factors and keep multiplying factors over factors will increase the sensitivity of your design and your model to extreme events.
Okay, very good. So the next question, also from Mir, is a slightly different topic. What does physics-based AI mean?
So as I mentioned in the previous question, so this is a new, I would say, paradigm for machine learning. Instead of having a link functions that are built into the system without accounting for the physical boundaries, you input actually partial differential equations and so on as your link functions, and it initiates the layers within your basically machine learning algorithm, and it tries to optimize obeying the physical rules. This is a very generic answer, but it's a long topic that requires a more detailed discussion.
Okay, very good. So Mustafa asked the following questions. From a pavement asset perspective, what are the major steps that we should take as an agency to factor in climate change at the design and maintenance levels? For example, using a higher asphalt binder grade or building a thicker pavement structure. Do you have any recommendations?
So it's really hard to give a single recommendation, to be honest. And what we are trying to achieve through this resilience-based design framework is to avoid thicker pavements for no good reason. So the best thing to do at this stage is to reconsider the analysis that we have and reconsider the design inputs at the beginning, and then see if there is a need for thicker pavements. And especially for pavements, since it doesn't always lead to, I would say, a life-threatening situations, it may be better to consider, maintenance activities down the road in some cases. So the short answer, reconsider the input loads, really have a full stochastic model for that. And I know that's not easy. And then try to see the cumulative damage impacts over time for repeated events, and then see if the design leads to a more, I would say, optimal design with thicker pavement or more maintenance activities spread out through the life of the pavement itself.
Okay, next question is from Rob. And would you agree that costs play a factor in based design.
100%. And that's where this slide showing the risk return analysis in here comes in. And this considers also the cost. And it's really hard when we talk about risk, it's cost, but there's also serviceability and human life. And it's a long discussion. We don't want to go into human life, but cost definitely is one of the most important factors when it comes to estimating returns as well.
Okay, the next question is from Kurt. And Kurt's question is, how are climatic models in current pavement design procedures, such as AASHTO's Pavement ME, accommodating more recent changes in climatic conditions?
Well, that for that specific question, I'll give a general answer, and I would refer to our Pavement ME group to give more detailed answer in the future if needed. But the current models do not necessarily account for all the details. They account for some variability and some changes. There are ongoing projects actually, one of them with ARA and some other entities that are looking at improving climate models. But I would say that considering all these repeated events, especially disruptive events, it's not necessarily part of the climatic models currently available. It's more of updating these trends, overall trends and changes. And again, I will defer to my other colleagues that work on Pavement ME for a more detailed answer.
Okay, then the next question, first a compliment from River, but the question is, do you know how current administrations and organizations such as AASHTO and FHWA are addressing the problem of increasing extreme events and disruptive events? And do you believe the current trajectory of improved design standards are on track to achieve effective resiliency and infrastructure over, say, the next 100 years? Wow, that's quite a question.
Yes, and that's that. My response will be sensitive, so I'll try. I'll be brief on this one because it's more of opinions rather than actual observations. But from the observations that I've seen, there are basically directions and efforts going in that direction. However, we are still far from agreeing on what really are resilience measures out there, and there is a lot of focus on very generic frameworks that talk about resilience processes and resilience evaluation, but there is still a gap when it comes to quantitative resilience-based design. But I believe that there is interest and there is an effort going on with Federal Highways and AASHTO that I'm aware of some of these efforts. But again, there is a lot of work to be done in there, and I'm not sure if we will. I'm confident that we, as human beings, smart enough to come up with a solution, hopefully, in 100 years. But that's a longer discussion.
Yeah, I might just also share is it takes a long time to develop something, but also to integrate it into mainstream practice is another issue. And I was intimately involved with the load resistance factor design journey. And through the development stage and the deployment stage, that took, I don't know, 15, 18 years. So be
Oh,
patient. Progress is slow. So Arash, forgive me if I mispronounce your first name. Next question is, assuming a consultant is developing an AI predictive model, how would you envision the review process by DOTs or clients, considering these tools are proprietary and often function as black boxes? Additionally, what level of accuracy will be considered acceptable? Again, these guys think you're very smart, and you are.
Oh, thanks for the compliment, and I hope that I'm smart enough to answer the questions properly. So, for AI applications, I agree. I've seen it over and over, trying to basically push that to agencies. I would say that there should be also other tools, such as currently, with OpenAI applications, there are some tools coming up now to test the outcomes of OpenAI. So there should be tools, and that's where, again, it's becoming a cliche here, but physics-based AI models can input these models and test whether they actually meet the physical requirements and they make sense or not. Considering physics and engineering is very critical when it comes to predictive models. Statistics is not necessarily, and I'm going to use the word statistics in the generic sense, since AI and machine learning builds on statistical learning. Statistics is not necessarily wrong or right, but it deals with the data as data. It doesn't really consider the engineering aspects and the physics. And it's the role of basically agencies, engineers, and other consultants to help agencies build a more robust engineering and physics-based tools that can test these predictions and that can basically put them to test and evaluate their validity. Now, in terms of the accuracy, there is no right or wrong answer for one big reason. Uh, the uncertainty evaluation and considering uncertainty in the predictions as well is going to be a critical role to evaluate the accuracy. However, when it comes to also the accuracy of the models, I would say the right answer would be to keep an eye on the asset over time and other assets over time and try to compare the predictions that we have or we have built through AI procedures with what happens in real life. And that's where also the Bayesian approaches come in to evaluate how far our models are and then improve them without, again, compiling over and over calibration factors over time.
Okay, great. And we do have a couple of more questions, but unfortunately, we're out of Q&A time. Ahmed will be responding to your questions if we didn't get to them, as well as you're welcome over the next 24 hours to submit additional questions. Everybody who is joined us for the entire hour, and we're obligated to follow that somewhat methodically just in order to keep our accreditation, receive a 1 hour PDH credit and a copy of the presentation. Allow us, please, a couple of weeks for you to receive your certificate. If you have any questions, you see the ARA webinar address shown on this particular slide. Okay, so a little bit of a commercial for those of you who are interested in working for a wonderful company. ARA is a wonderful company that I'm referring to. We're a national firm. We're always looking for great people to join our team. And as shown in this slide, we really strive, and we're true to our mantra. We hire valuable colleagues, not only with the right skills, but those of you who share a passion for freedom, service, and growth. These are our core values. And we have a number of exciting opportunities. If you're interested in employment opportunities with our transportation and infrastructure offices, we have a number of business lines, but specifically for transportation and infrastructure, please send a brief resume and contact information to the address that you see here. So with that, thank you all for joining today's program. Ahmad, great presentation. May God bless you all. Have a wonderful day.